Good morning, everybody. Those of you that are here in person, as well as there's already 48 people online. So it's great to have a great turnout. Today, we have the honor and privilege of listening to Dr. Frank Harrell. He received his PhD in biostatistics from the University of North Carolina in 1979. He was a faculty at Duke University at the Duke Clinical Research Institute for 17 years, and at the University of Virginia for 7 years. He was the founder of the Division of Biostatistics and Epidemiology at the University of Virginia School of Medicine, and also the founder of the Department of Biostatistics at Vanderbilt University in 2003, where he is located right now. He has taught biostatistics and research methodology to hundreds of physicians since 1980 and has been a mentor or co-mentor to several physician investigators. He's an associate editor for Statistics in Medicine and an advisor to the U.S. Food and Drug Administration. He specializes in the development of accurate prognostic and diagnostic models, model validation, clinical trials, observational clinical research, technology evaluation, quantifying predictive accuracy, missing data imputation, pharmaceutical safety, flexible Bayesian design and analysis, statistical graphics and reporting. So I call him the Renaissance man of statistics for his breadth and depth in his applications. He's also well known for being the author of sort of the Bible of regression modeling strategies that we all use in our courses. And today we have the honor of listening to him talk about Bayesian thinking and why it's very different from what we normally have been taught how to think. So I'll leave you with that.
Thanks for the nice introduction, Shrikant. We were classmates at UNC, so he's been a wonderful person to know for a long time. Always a good guy. I did want to mention that this is a bestseller on Amazon, and the last time I looked, it was number 275,000th bestseller, right after A History of Nausea and Vomiting in the South. So good to be on that list. But I'm very honored to be here today, and I'm thankful for the invitation, and I'm really honored to do this in the memory of Janice Pogue, who was a very esteemed statistician and much loved, very accomplished, quiet spoken, but would stand up for what she believes in terms of research methodology and statistics and other things. So we really miss her. I was not fortunate enough to know her in person, but I've talked to a lot of people who did, and she has left behind just beautiful feelings and memories. So see if I can move this little thing. Oh, here. So there's a lot of room I've left for discussion for this talk, and I hope people will really feel free. So this talk, like most of my talks, is I sort of follow the lead of a great newspaper that said their role is to irritate 10% of their readers. And so I probably irritate more like 100% of people in some ways. But one of the reasons we tend to get irritated when people have alternate viewpoints is we have sort of investment costs. We've invested in certain ways of doing things. And when I was at University of North Carolina with Shrikant, they were actively disdaining Bayesian methods, and I believed what they said. I was really wrong at that point, but I believed it. And they would say, you know, that Bayesian method is no good. Don't waste any time with that. And so we were taught only the classical approach. And so it wasn't until I had been actually in a real job for about 16 years that I really started understanding the Bayesian viewpoint and why it should be used. The single thing that got me over the edge, and I've written a long blog article about my journey from frequentism to Bayesian on my blog. The single thing that got me over the edge was trying to understand group sequential trials group sequential statistics. What are the stochastic processes in play? What are the sampling distributions, and how do you do alpha spending and all of those things? I found it very difficult to understand. And when I started reading the works of David Spiegelhalter, the eminent Sir David Spiegelhalter at Cambridge University, he had sequential monitoring of clinical trials using a Bayesian approach. It was actually trivial. I mean, it was instantly understandable. So when I saw that difference, and I had trouble understanding, why do you need to learn about a Brownian motion and Brownian bridge when you're doing sequential testing and various statistics? I saw that you don't need any of that. So the need for things like stochastic processes when you're sampling in a sequential fashion comes from the fact solely that you're interested in a sampling distribution. And once you're interested in a different dimension, which is the parameter distribution, that deal about sampling and optionally stopping a study, it totally disappears. So I've never seen a clinical trial published where the correct sampling distribution was used for the final point estimate. And you know that when you have optional stopping, the sampling distribution might be bimodal. It might have a discontinuity in it. And the confidence intervals we use are not valid when you ignore the fact that you might have stopped the study early. If you look at what that does to a Bayesian posterior distribution, it doesn't do anything to it. It's just a posterior distribution. It doesn't matter when you calculate it. There's no stochastic process that you have to deal with because the current posterior probability is all inclusive. So some people have written about Bayes that it's so boring because you have a unified approach to things. And once you put your problem in that machinery, you just turn the crank. You know, the only argument is the choice of the prior distribution. And other than that, it's very, very boring. And you don't need to spend your time with all of these complexities that come from sampling distribution because there's no sampling distributions in Bayes. So everything is different. So I'm going to be explaining, you know, some of the why and then what are the implications of those differences. So we get into the basics here of Bayes' rule. And a lot of physicians are exposed to Bayes' rule pretty early, and they're taught it when they're learning about probabilistic diagnostic medicine. And so they're taught how to do a reversal. So this is just a reversal of conditioning. And when Bayes derived his formula, you know, that was actually an easy derivation, just using the laws, basic laws of probability and what it means to have a probability of the intersection of two things. What does a conditional probability mean? And so this reversal would say, if you know the probability that a symptom will be present given disease is present, you can reverse that to get the probability disease is present given the symptom is present by multiplying by the prevalence of the disease, the background prior probability of disease, which is actually not defined. People think they know what prevalence of disease is, and they don't really have the best definition of that. And what's the prevalence of pregnancy? Is it X or is it X over 2? So is it sex specific? You know, that's a ridiculous example, but when you talk about prevalence of flu, that's not even that well defined. Are you talking about the flu in adults in care facilities or kids in child care facilities or general population, whatever? So, and then divided by the probability that the symptom is present, whether or not the disease is present. So that's an unconditional probability, and that's the one we care the least about. And the way that you usually see Bayes' formula is the way you calculate the probability the symptom is present. It's the sum of probabilities, whether you condition on disease being present or not. And it's just using the law of total probability. But that just adds up to the overall probability that the symptom is there, whether or not the disease is there. And now, a funny thing about introducing people to Bayes this way, the most simple part of Bayes is the formula. And it's the least important. The most important part of Bayes is Bayesian thinking, which is what this talk is all about. When you start thinking Bayes, you think totally differently. And depending on who you believe, when people study how the human brain evolved, it's a lot of Bayesian updating, Bayesian learning, and how we make decisions is mainly Bayesian. We're weighing risks and we're deciding, do you cross the street when there's a little bit of traffic? We do kind of a risk-benefit analysis, but what's in our mind is the probability of being hit by a car. So it's the forward probability that we're interested in. I think Bayes' original application, if I remembered right, was in the game of billiards, where you know where a certain ball ended up and you want to back reason to where the ball started before you hit with the stick. And so people are using Bayes in a very similar way, in a very exciting way in neuroscience, where you know that if you stimulate the big toe, you can measure the brain activation region for that nerve. But what if you measured brain activations and you want to back reverse engineering to what stimulation led to that brain activation? So they're using Bayes' rule. People are using Bayesian thinking, like when there's a plane crashed and you know certain information about the plane before it crashed into the ocean, and you're using Bayesian methods to backtrack to learn other things about the flight and to try to learn where it ended up in the ocean. Now, this is really an odd application of Bayes' rule, and I irritate a lot of physicians when I tell them that Bayes' rule should not have actually been used in that example. It's one of the worst applications of Bayes' rules that I can imagine, because this is a case where you would estimate the probability of disease given a symptom directly from data. And to use Bayes' rule implies that you are in the case control study mode. So you have a case control study in which you sample 50 people with disease, 50 without disease, then go and do a test and see if it's positive or negative. That means you have these conditional probabilities here from a case control study, but then you have to fight with this. So that's not actually a very natural use of Bayes' rule unless you're living in a case control retrospective study world. If you're living in a cohort study world, you have no place for Bayes' rule for diagnostic medicine, because in a cohort study, you estimate this directly. So that's just what we call logistic regression. So you would have symptom as a covariate, but you would do way better than that because you would also adjust for age and other symptoms. So that's a direct probability model from a cohort study. It's a cohort study being prospective. You don't condition on the outcome to get into a cohort study. You might condition on an age range and maybe having at least one symptom out of 10 or something like that. But when you have a cohort study, you just start with this and you stop with this. So I've seen medical docs take a 2x2 table where you have symptom, you have disease. They calculate sensitivity and specificity, use Bayes' rule to calculate probability of disease. They just think about how shocking that is. You're driving a car, you need to take a right turn, so you take 3 left turns. There's no way that that's the way to drive a car. But I've seen that actually done, even in medical education. So that's a real side issue. But you could use Bayes' rule if you had a case control study to give you this. And then how do you correct a case control study for oversampling? You have to know more. And Bayes' rule will do that for you. When you talk in general, we have some probability about an unknown quantity, and I'll just use theta throughout. At theta could be a difference in means. It could be an odds ratio, risk ratio, hazard ratio, anything you want. It's something you don't know. It's something that generated the data, but you don't know what it was. It's like a treatment effect. So just using the same notation, you have the probability of the data given as if you knew what generated the data. And so this is the heart of what we do with Bayesian inference, because this is easy to write down. So if you suppose that theta was fixed at a single number, and just call it theta, but theta can stand for any number. you can write down this likelihood function in standard way. Like if you're flipping a coin, you know, you've got theta to the y, 1 minus theta to 1 minus y, that's your likelihood. So this is easy because that's your standard thing that you do in frequentist statistics. And then you have this prior distribution for theta. This is like prevalence of disease. And then you have something you really wished wasn't even there, which is the unconditional probability of the data having arisen. So the probability of the symptom being present, whether or not you have the disease. That's of much secondary interest and almost impossible to get. So what happened in the Monte Carlo, Markov chain Monte Carlo world, when Bayes actually started to make great headway is when the computational problems were solved. So we didn't have to assume something so simple about these things that we could calculate this analytically. I'll give you one example where we do calculate it analytically. It's very simple. But in general, we don't know that. So just think about you're doing a logistic model and you've got an odds ratio and you have prior information about the odds ratio. The way that we express prior information about an odds ratio is usually we know something about where it's centered and it's spread. And so we state it on the log odds ratio having a normal distribution. So that's the most common prior that people tend to use for an odds ratio. Log odds ratio has a normal distribution. And when you put that in for P here, none of this simplifies. And you need simple simulation methods to calculate your posterior distribution, even for a basic logistic regression model. But what happened with Markov chain Monte Carlo and related methods is people found 50 or more years ago that if you wanted to sample from this distribution, all you need is something that's proportional to the right answer. You don't need the right answer. So these just become weights in a sampling scheme. And if this is completely impossible to calculate and you may not even know how to go about calculating it, it doesn't matter because it's just a number that you don't know. So if you sample from the posterior distribution of theta, you're sampling from this product. And you need to weight those samples by an unknown weight that's here. But in terms of Gibbs sampler and all the other methods that are being developed, you don't need to know those weights. So we're getting the right shape of the distribution of the posterior, and we're getting valid samples from that distribution without knowing anything like this. So all we need to use is that this probability is proportional to this product. Now, when you imagine the implications of this, it's actually vast. I want you to look at what this symbol means. That symbol means what it means to a third grader. That's a simple multiplication. That's multiplying two numbers. This is not vector calculus. This is not a stochastic process. This is not Brownian motion. This is nothing like that. This is a third grade scalar multiplication operation. So all of Bayesian inference is based on a simple multiplication. Why is that profound? That's profound because if you look at what it takes to calculate a p-value when you've done sequential testing, you cannot calculate a p-value. P-value doesn't exist when you have sequential testing. All you have is stopping boundaries. Did you exceed the stopping boundaries? And overall, you'll have an alpha probability of ever exceeding the stopping boundaries if the null hypothesis happened to be true. So we have cutoffs for rejection and decision-making in sequential testing, but you don't get a p-value from that process. And in other cases, the p-value is so hard to calculate, but it's calculatable. We can still calculate it, but the formula for it is a nightmare. So if you were to calculate a p-value for a random effects model for a fixed effect, the fixed effect is very simple in a random effects model, but the p-value, if you tried to calculate that, it's very hard. So we use numerical integration that is no easier to do than anything in Bayes, and it's not fully accurate. So whenever you use a mixed model, everything you're using is an approximation. And we have some recent studies showing how certain mixed effects models do not preserve alpha. So there's more to that than you think. And p-values are not always as accurate as you think, but the bottom line is the calculation of p-values can involve a high dimensional integral, great complexity, and the calculation has to involve intentions. So the classic example is if you sampled until you had 10 heads, and that took you flipping a coin 21 times, versus if you planned to flip a coin 21 times and you happen to get 10 heads, and you wanted to test some null hypothesis, you'll get much different p-values. The data are identical for those two experiments, but one of them has a negative binomial distribution, another one has a binomial distribution. So your p-values are going to differ because of the intention. So the p-value involves in its calculation the intention of the investigator. And we mentioned yesterday that it's still amazing in Fisher's initial work where he talked about p-values, the lady tasting tea, is from Fisher's information, it's impossible to calculate a p-value because you cannot tell whether the lady was given a fixed number of trials or whether the experiment was to go until she said five trials had the milk put in first. You cannot tell that from any of Fisher's writings. And without knowing that, you cannot calculate a p-value. So that goes back to the amazing thing here. You don't have any of that stuff. All you have is what is truly a scalar multiplication problem. Notice the absence of calculus here. So Bayesian methods respect the flow of information and the flow of time. The data are known and theta is not. And this is really the whole deal. You're reasoning from what you know to get to what you don't know. And that is what is drastically different with Bayes. And you can make use of pre-data knowledge. We always have some kind of knowledge about theta. Always. It may be a general knowledge or it may be specific knowledge. Specific would mean you've done earlier experiments and you've already got a rough estimate of theta. That would be data-based knowledge. And then you have non-data-based knowledge, which would be there's a new therapy that's trying to alleviate suffering for patients with an incurable disease, and your outcome is mortality. So in that case, you know the odds ratio is impossible to be zero. It's an incremental therapy. So you know whether a therapy is curative or incremental. A curative therapy can have an odds ratio of 0. Incremental therapy cannot have an odds ratio of 0. So that goes into your prior distribution. You always know something. It may just be general medical knowledge. So this is a typical representation of results. This is as applied to a clinical trial. This was a paper that we just published recently that I think is a pretty good introduction to Bayes and a lot of information about choosing priors and so on. And so what you have is your state of prior belief before you have any data. Now this prior is saying that we believe there's a little bit of harm more likely than not. This is kind of unusual that we would have a study with a prior like that, but you could do it. So we're allowing for a slightly more belief in harm than in benefit. And then you have your likelihood function. So your likelihood function here is that probability of the data given theta piece. So that's a very easy thing to calculate. And it is not influenced by prior information. And then when you allow it to be influenced by prior information, you're going to go somewhere between here and here to get your posterior distribution. So now this is your best psychological, in terms of cognitive psychology, this is your best presentation of the results because this encapsulates uncertainty. And it says that we have more belief of values in here, but we have this amount of uncertainty. So by having this as a graph rather than an interval with bars, a confidence interval gives you limited information, and it sort of implies that all values are equally likely within the interval, which is not true. This doesn't have that problem. And so when this is an absolute risk difference scale. Benefit negative, harm is positive. And this is the posterior distribution after you collect the data. This is a region of practical equivalence, ROPE. So we just said -1 to +1 absolute risk difference is a region of similarity of the two treatments. They're practically equivalent. So you can calculate the probability that the treatments are practically equivalent. You can calculate the probability that the benefit is the benefit of achieving the minimum clinically important difference or better. That's the area to the left. And you can calculate the probabilities of harm, which would be areas on the right. So you see, once you mark off the clinical thresholds, you can calculate probabilities for any interval of interest. Now think about a confidence interval. Confidence interval is out of your control. Confidence interval, you give it the probability and it gives you the two numbers. The way most subject matter scientists think is I have some clinical knowledge of what are interesting points of efficacy. I want to give you the points and you give me the probability. So you have control of the points, the limits, the interval, and then Bayes will give you the probability of that interval containing the truth. So you have control over the limits. So the limits are in clinical units, whereas in a confidence interval, you have this coverage probability that's kind of hard to deal with. And it automatically gives you limits, and those limits might be not concentrating on what you're actually interested in. One other point to think about, there's a lot of discussion in the Bayesian literature about what a non-informative prior means. And it's non-informative on what scale? Is it on the logit scale? Is it on the probability scale? And you'll get differences depending on in what scale you have flatness in the prior. To me, it's better not to think about any of that stuff. So when you get familiar with the world's greatest Bayesian software, which is STAN out of Columbia University in New York, you'll see that if you don't give a prior to something, the log likelihood function is never modified. So you give the log likelihood function and it will give you the posterior distribution from that. It doesn't add anything to the log likelihood from a prior. So I think of a non-informative prior as just, instead of saying that, I want to say there's no prior. So the absence of a prior means we're not augmenting our knowledge with any other source of information. And don't talk to me about scales or anything. I'm just omitting the prior. So the STAN software will just not modify the log likelihood when it gets to posterior. So this is the posterior, if you had no prior, is going to equal this. So the prior is not there. That's, to me, easier way to think about it. And when you're looking at the Bayesian calculations, the prior is just like having data. It's interchangeable with data. So when you're adding the log of the prior to the log of the likelihood, it's like adding data. And in simple cases, and Sander Greenland, the great quantitative epidemiologist, has written extensively about this. In simple cases, you can solve for what data you need to add that will give you a certain prior. That's called data augmentation. So it's a very appealing way to think about it. It doesn't generalize to complex parameters and things. It's the main reason we don't do it. But you can think of the prior as augmenting. So if your prior was that it's not very likely this treatment does very much, let's say that let's say it's a simpler case, a coin toss, and your prior information is the coin is more likely to be a fair coin. the prior distribution can be encoded by just creating, let's say 10 or 20 coin tosses that came out 50% heads. Putting those data in with your raw data has the same effect of having a prior that's concentrated at 0.5. So there's some interchangeability there. So how do you state results? So we've got a randomized clinical trial comparing two treatments. It's a parallel group randomized trial. The observed mean difference in blood pressure is 5 millimeters of mercury. The unknown mean difference is theta. So the p-value, we usually test against the null hypothesis. Why that's true, it's kind of hard to understand. And let's say we get a p-value of 0.02. What does that mean? That means the probability that someone else will get a difference greater than 5 in their data, given that our null hypothesis is true for them. So think about that. The probability of observing data as impressive, more impressive than 5, is the p-value. So you're talking about the probability of observing someone else's data given your null hypothesis. So that's what the 0.02 means. So it's the degree to which the null hypothesis is embarrassed by the data. That's the most general way to state a p-value. And I forget whom to give that attribution to. It was a wonderful quote. And then you have uncertainty intervals like confidence intervals. And the problem with them is people can't really define what they mean. There's yet another paper came out this week talking about this. It's an endless stream of papers about what confidence intervals don't mean. And so they only have long-run operating characteristics, whereas what we want to do is to make probability statements about the current data generating mechanism. So what is the Bayesian? Well, this is a way that I would do it myself, is to keep it simple. You know, Bayes is not about, until you get into Bayesian decision makings, which requires a utility function, Bayes is about playing the odds. It's about informed judgment, minimizing your risks. So if you read Nate Silver's book, The Signal and the Noise, it's all about Bayesian thinking. And if you think about things in a Bayesian framework, you'll make a lot of money in betting on basketball and other sports as he did. And he talks a lot, and we were talking about this the other day, about how poker players think in a very Bayesian fashion, makes a lot of money for them. So the treatment B probably, and I would expand on this in a footnote, it probably, parenthesis 0.97, lowers blood pressure. The probability of theta is greater than 0 is 0.97. And of course, you have to say, given your prior distribution and your model, and then you can get an uncertainty interval. Most people prefer the highest posterior density uncertainty interval because it has the property of being the shortest interval with that amount of coverage. And so you could say the probability is 0.95 of the unknown data generating difference in means, the unknown, or we could call it population difference in means, being between 3.5 and 7.2 is 0.95. So now we have a 0.95 probability that we can assign to that interval, instead of saying that if you did infinitely many intervals, so many of them would happen to cover the true value. We're interested in the data set we have. Right at this moment, we're not interested in anybody else's data set. So here's a real example that I encountered recently at Vanderbilt. We have this medical record system called Epic, which, to the best I can tell, is a way to move a lot of your profits from your health system into a software company, because they charge, for one medical center, they may charge, you know, $230 million. I don't know what it's the average. It's totally unbelievable what this company is making. They're based in Madison, Wisconsin, and Dave Demetz gave me a tour of their campus once from a distance, and they spare no expense, I can tell you that. Oh, I didn't know it was used in Canada. So Canada's got money after all.
Any hospitals.
Really? Well, Epic is in a unique position of dictating a lot of things. And if you watch what they do, you better watch out, because like they launched with no validation a model for the probability a patient has sepsis. And people immediately found that model was not to be trusted. Epic apparently can do things without quality control. They just do it, just implement it. And you better watch out. And here's another example. They have this thing called the coin toss. And we have an ongoing study in our learning health system where we're trying to do one-to-one randomization. And it's actually, since this was written, it's gotten worse in terms of the imbalance. So we're not getting one-to-one randomization. And is this something we should worry about? What we'd like to know is, what is the inference about the data generating process? So the data generating process is a random number generator. And if it's less than 0.5, they assign to one treatment, greater than 0.5 to the other treatment. So we're trying to make an inference about that procedure. Now, we know the numerical algorithm they use, and it's one that's been validated fairly well, but we don't know about how they programmed it in their software and whether there was a problem in how they implemented it. Like one example of a problem you could run into is, how do you initialize a random number seed? So this is a non-reproducible process, which the statisticians at Vanderbilt are putting their foot down to say we should not be using non-reproducible processes. There's no random number seed that somebody has locked away that could reproduce everything. So how did they start the process off? And did they happen to make a mistake so that once you start randomizing people, maybe you, by accident, go back to some original random number seeds, so the process is not independent anymore? So I have no idea that happened. It's just an example of what can happen. So this is where things stood. It's 130 to 94. And one of the reasons I got concerned about this is when you write this up and submit it to a journal, journals reviewers tend to raise questions about this thing. Didn't you say you're doing one-to-one randomization? Now, a good statistician knows how to do randomization. And what a good statistician does is they generate a perfect randomization. So you would generate a randomization that has exactly 100 people in treatment A and 100 in treatment B, and then you randomize the order of those assignments, and that's your randomization. So you can do that stratified, you can ensure perfect balance, and it's just going to be perfect. We don't get into this problem, but this is an epic problem. So we have an intended one-to-one randomization. Is the randomizer defective? And what's the difference between addressing this in a frequentist way versus a Bayesian way? So in a 2x2 table, and doing a null hypothesis of a half, you get a p-value of 0.019, and the accurate Wilson confidence interval is 0.51 to 0.64. Now, I work with a lot of smart clinicians, and one of them made this mistake, which I'm sure you've made because I've made it myself. And the clinician said, you know, I'm not that worried about a 0.019 because that means that just by random chance, I could observe a randomization breakdown like we observed almost 2% of the time. That's not what a p-value is. So a p-value is not even what we tend to think it is, even if we are pretty educated about a p-value. That's not what that p-value is. So what the history of this, which I wish I knew the details, is Fisher came up with the idea that a p-value is the probability of observing something like what you observed, given a null hypothesis is true. And then he did some calculations, and all the probabilities were tiny. The probability of observing a 2x2 table that you observed is tiny. So he said, we're always going to reject the null hypothesis. Something's wrong. And at that point, he actually made an ad hoc correction and said, the only way not to get a p-value that's always tiny is to pool that result with more extreme tables. So it's no longer the probability of getting a table or a result as extreme as yours. It's not that anymore. Hasn't been for a long time. So the probability of getting results as extreme as ours in either direction is what Fisher started out with. If you have a continuous outcome, that probability is 0. So the probability of getting a difference of means of 5.2456 given a continuous distribution for blood pressure, that probability is 0. In a discrete case like we have, our randomization is count data is discrete data. So this is not necessarily 0. So the p-values are probably getting results as extreme as ours in either direction, plus the probability of getting results more extreme. So how much of the p-value is coming from those two sources? It's this. So as I said, in the continuous case, that first number will be 0, and every bit of the p-value comes from someone else's data, not your data. So you can see even in this case, 2/3 of the p-value is coming from data we did not observe. Isn't that problem enough with the p-value? The problems get much worse than this. But this to me is just about enough to know that we have a problem. And it also ignores clinical versus statistical significance. So what's the evidence for a defect? First of all, you realize we have prior information. When you think about it, you always have prior information. So what is the prior information we have here? So you have to think like the best role model for a statistician in the history of the planet is Sherlock Holmes. My role model is not Bayes, Fisher, Box, Tukey, any of those, as great as they are, but my role model is Sherlock Holmes. And if you watch some of the great shows or read the books, you know, the reasoning of Sherlock Holmes, for example, he's looking at something that somebody who disappeared, they wrote on a piece of paper, and he sees that the handwriting is nice, and then every few lines, the handwriting gets bad, then the handwriting gets good again. So he surmised that that person was riding a train, and when they were stopped at the station, the handwriting was good, so he could tell how long he was stopped at a station, and he ended up tracing out his whole route. So that's thinking. You know, that's what we need to be doing. So what prior information do we have here? Theta is unlikely to be outside the interval 0.4 to 0.6, or somebody would have noticed. It's not the kind of prior information you have like prior effects of a treatment. It's nothing like that. But it's just using logic. You know, if it was extremely bad algorithm, you would have seen it like in the first 50 patients randomized ever. So we're going to use a prior distribution that says theta is unlikely to be outside the interval. So we're going to use a beta distribution, and we're going to make it a symmetric beta distribution, which means the alpha and beta parameters have to be the same. And so we're going to make it so the probability that the unknown truth is within the interval 0.4 to 0.6 is going to be 0.9. And when you use that beta prior distribution and you have a binomial data distribution, you have a beta posterior distribution, very simple. And the Bayesian posterior probability of being more than 0.02 defective is 0.93. And so this is my summary of the evidence. So this is a summary of the evidence that's on the actionable scale. It brings in clinical significance because if your randomizer was randomizing 0.501 to treatment B, and if you had enough replications, you would get a significant p-value. Nobody cares. If you claim it's 0.5 and it's really 0.501, you're not at the null hypothesis anymore, but nobody cares. So I just figured myself, I made this up, that what we would care about would be a defect more than 0.02. And that goes into the posterior probability. So we have clinical significance, we have exact calculations, and interpretability. So we have evidence for a non-trivial defect in the randomizer. And this is what our prior distribution looks like here in blue. We have our distribution ignoring the prior is shifted over here. And then the prior is going to pull that back. And so when we're claiming something to the rest of the world, we want to claim this middle distribution, the red one, because that one is made to be more realistic because it's incorporating our prior knowledge. All right, now I've got a bunch of miscellaneous remarks about Bayesian versus frequentist. Do you want to know the probability of a positive result when there is nothing? That's what alpha is telling you. Or do you want the probability that a positive result turns out to be nothing? Those are just slightly different words that couldn't have more different meaning. The probability that something turns out to be nothing means that you claim there's efficacy, or you claim that a certain risk factor is a risk factor, and it turns out you were wrong because the real effect is zero. So that's something that turns out to be nothing. That's called a decision error. The first thing is an assertion probability. The second thing is a decision error, and that's all we care about. So Bayes quantifies evidence for every possible value of theta. Hypothesis testing in the frequentist world allows you to build evidence for what theta is not. We care a lot more about what theta is than what theta is not. But in the Bayesian world, you can look at the evidence for all possible values of theta from one analysis. So frequentism is about a process, an endless stream of samples. Long-term operating characteristics are emphasized. So the alpha value is a probability of ever asserting a positive effect over the course of your study if you're doing sequential testing. And that alpha is not a function of data. It's a pre-study concept. It's a pre-study long-term operating characteristic probability. Has nothing to do with anybody's data. It doesn't use data in its calculation. So why should we put so much interest in something that doesn't even use our data? Bayesian deals with uncovering hidden truths in the process that generated the current data set. To me, that's a bit more relevant. And that also allows you to draw inference to population quantities if you want to think in the more usual sampling from a population frame. So the Bayesian approach gets criticized for needing a prior distribution. So it has to go out on a limb. So it has to bring in this prior distribution in the multiplication that you're doing, the simple multiplication, to answer the original question. Is the effect greater than some number? The frequentist approach stays close to home, keeps things simple. One reason was so that Fisher could do calculations with pencil and paper. The model is so simple when the null hypothesis is true in many cases. You can do hand calculations. So you stay close to home. You don't need to quantify prior knowledge to answer an easier question, but it's an almost irrelevant question. How strange is my data if the null hypothesis were magically, stunningly, amazingly true? So it's simple because you're kicking down the road the tough problem. So John Tukey had so many quotes. One was better to have an approximate answer to the right question than the right answer to the wrong question, no matter how well specified. So the way I translate that is if somebody doesn't like your prior, they're going to get a different posterior probability than you. So there's going to be, they would see your answer as approximate. The two answers are going to be surprisingly close together anyway. But the second person will see your answer as approximate, but you're trying to answer the right question. Does the treatment work? I don't want to answer how surprising the data were if the treatment doesn't work. So I see the Bayesian approach to the critic, it's an approximation, and the person who criticizes your posterior distribution, the probability is 0.97 instead of 0.96 because we have a difference of agreement about the prior and the sample size is fairly large. They are not being genuine. So if you're going to be a genuine person and you're criticizing another person, you have to look at your own self. How accurate are your p-values? The p-values are are often not as accurate as to within plus or minus 0.01. So the critic criticizes the prior and takes the p-value as if it was calculated correctly. And it usually isn't, except in simple normal distribution cases. So you have to subjectively convert observations about data to evidence about parameters in the frequentist world. And where that leads to most problems is if you have multiplicity corrections, endless discussions about how this translation takes place. Because in a multiplicity correction, there is no principle that tells you which multiplicity correction to make. It's totally ad hoc in practice. So what if you were building a smoke detector? What would a frequentist smoke detector look like for your home? So you might specify alpha is 0.05. That would be the chance of the alarm going off in your home when there's no fire. Now that may sound interesting, but I really don't think it is. What's a Bayesian smoke detector? The probability of fire given the air characteristics. And then if we wanted to have rational decision-making, we would set the threshold, and different people would have different thresholds. They should be able to use their thresholds in their home. We'll set the alarm to trigger when the probability of fire when people are at home exceeds 0.02, or when they're away, it exceeds 0.01. So we have different cutoffs because if you're away, you can't check to see if it's false alarm. You have to take quick action in the absence of people. Now, what about the way, if you were a frequentist doing clinical trials, how would you design a smoke alarm? So you know people are still using power of 0.8 in sample size calculations. That should be outlawed. That is just meaning a 20% chance of a false negative assertion versus a 0.05 chance of a false positive assertion. That 4-to-1 ratio makes no sense whatsoever. But not only that, a lot of clinical trials, and this is really true in single investigator or single site clinical trials, they pick an effect size that's like triple the MCID because they can't afford the trial if they target the power at detecting only a 5% mortality reduction. So they're powered to detect a 20% mortality reduction. So that translates to a smoke alarm that says if there happens to be an inferno in your house, it's already half burned down, and the fire is putting flames 50 feet into the air, you have an 80% chance of detecting that. That's the exact analogy to how we do most clinical trials. Doesn't make any sense. So the type 1 quote error, which has nothing to do with making an error, so probably asserting an effect when there's no effect, it's independent of data. Whereas if you calculate the probability that a treatment works in the right direction, 1 minus that is the probability that it doesn't work. So the probability of inefficacy is 1 minus the probability of efficacy. So this is your probability of being wrong or making a mistake, making an error. This is the probability of a decision error. What's the probability you've drawn the wrong conclusion? This is the probability everybody should care about. I don't want to know the alpha operating characteristics of some sequential study. I want to know the probability of getting the right answer. Alpha in the frequentist world has nothing whatsoever to do with the probability of getting the right answer. So what about replication? Replication is essential, and Fisher said a large p-value is interpreted in only one way: get more data. There's no conclusion from a large p-value other than get more data. And of course, the whole basis of frequentist is based on repeated sampling. How do you know if an experiment is even worth replicating? Why is it worth the resources of replicating something where the treatment effect was not very good? We can't just replicate things. They cost money and time. So you need evidence before you try to replicate something. So how do we judge what we have now before we have repeated sampling? Bayes is all about that. What about sample size? Frequentist world, you assume everything, even the minimum clinically important difference. we'll make an assumption that physicians actually agree about that. And like we were talking the other day, they don't agree with that. There's a lot of uncertainty. You could put that uncertainty into your Bayesian power calculation. The sample size is fixed, and you can spin alpha against that fixed sample size, which is one reason you need it to be fixed. With the Bayes, you put uncertainties around everything you don't know, possibly including the MCID, the effect size you want to be able to detect, and you make the sample size the random variable. So recognize and be honest. What's the random variable here? It's the sample size. It's the thing we actually know so little about. We may know more about the efficacy of the treatment than we know about the sample size before we do the study. So we want N to be big enough so that we have enough evidence to make a decision. And one of the things that makes the huge difference with Bayes is stopping way earlier for futility. You can sometimes stop earlier for efficacy, but you can stop way earlier for futility. Save a lot of resources. What about multiplicity? What's the source of multiplicity? It has two sources. It comes from chances you give data to be extreme. So if you do a sequential looks with 10 looks, you're going to have a higher chance of at one of those looks, the data being more extreme, like the difference in means. And it also comes from detaching clinical and statistical significance. In other words, it comes from testing null hypotheses instead of testing against something that's not zero. Once you start testing against something that's more impressive than zero, the alpha problem goes away. So most of the alpha problem comes from testing against zero. In other words, allowing yourself to be impressed by a trivial effect. Once you make yourself be only impressed by a non-trivial effect, even in the frequentist sense, the multiplicity problem virtually disappears, even in the high dimensional case, such as functional MRI with 10,000 voxels and getting 10,000 p-values. Test them against an odds ratio of 1.2 instead of an odds ratio of 1, multiplicity disappears. You get no multiplicity from sequential looks. The new looks merely make previous looks become obsolete. So I have this football example that tries to bring out this issue using real data. And so the frequentist world would say, if we're going to be looking at a football game a lot of times during the course of the game and making decisions, is it safe to turn off the TV because the team that's ahead by 10 points we think they're going to go ahead and win the game? When is it safe to turn off the TV? That's our decision. And the frequentist world of looking at multiplicity like we do in group sequential trials says that if team A ultimately ties or loses, what's the probability that team A was ever ahead, not head, but ever ahead by 10 or more points? And that probability has to go up as the number of looks increases. So remember, we're thinking about assuming a null hypothesis is true, working sort of backwards. That's the frequentist approach. So when you think about it that way, you're definitely going to have a multiplicity problem. And here's a graph that shows that in a minute. And the Bayes says, look continuously, stop watching the game the instant the probability exceeds 0.9 that team A will ultimately win the game. There's no multiplicity whatsoever from that issue. So this is the relationship between the number of looks and the probability that your team will ever be ahead by 10 points if they ended up tying or losing the game. So this is the frequentist look at the continuous watching of a football game, exactly as you would run a group sequential trial. So if you looked at the game continuously, which I just put as 125 looks, so you're looking, twice a minute, and you're assessing the score, you've got a probability of 0.15 of your team that ultimately tied or lost at some point in the game being ahead by 10 points or more. And then if the number of looks gets smaller, you see if you only looked twice, the probability of ever being ahead, which would be called a false positive by some, is more like 0.075. So this has to go up with the number of looks. You've given the data more opportunities to be extreme. What's the Bayesian counterpart to that? If you have a stopping rule that's 0.9 and you stop as soon as the probability of ultimate victory exceeds 0.9, over 1,985 NFL games analyzed, the mean probability for those occasions where we stop watching the game when the probability is greater than 0.9 was 0.913. So the question is that needing to be corrected for multiplicity or is it calibrated? And the answer is it's calibrated, because if you take all of those occasions when the probability is greater than 0.9 and you calculated what proportion of those games when the probability is greater than 0.9, did that team ultimately win? It's exactly 0.913. I didn't fake that. I mean, it's a testament to the NFL risk prediction model that they derived for football. Continuous updating model is a really well done, accurate model. Of course, it's trained on a lot of data. So the average probability is 0.913. The actual fraction who won is 0.913. The number of times that you calculated the 0.913 or whatever it was is completely irrelevant. So what happens, a lot of frequentists ask Bayesians to show what alpha is. We've just shown alpha is irrelevant. It could not possibly be more irrelevant to this problem. But a lot of frequentists are still asking Bayesian trial designers to show what alpha is. And then once the alpha, if alpha is not so-called preserved, they'll want you to have fewer looks at the data or no looks at the data. Or they want you to use some crazy cutoff on the posterior probability. So asking a Bayesian to calculate alpha is like telling a patient the specificity of a test that he already underwent. Specificity sensitivity is going to be of no relevance once you have the test result in hand. It's like asking a poker player who wins $10 million a year to justify his rankings by how often he places bets in games he didn't win. That's the alpha equivalent of judging the poker player. It's like judging a politician by how often he speaks when he's honest instead of how often he lies when he speaks. Most people would say the latter one is the more relevant quantity that we would use in judging the politician. So that's the Bayesian probability. So what about a t-test? You know, just maybe give a couple of examples and we'll have hopefully a lot of time for questions. In the frequentist world, we have to agonize over normality or equivariance. And when we do the Welch t-test, it's not giving us exactly the right p-values. So what about the Bayesian world? You add parameters for things you don't know. So the Bayesian t-test has a parameter for non-normality and has a parameter for the variance ratio. You put priors on both of those. You may favor normality when the sample size is small and you don't know much. You may favor equivariance, but you have a prior distribution on the variance ratio and you get exact posterior distributions and you'll get uncertainty intervals that are wider by the exact correct amount. If you get confidence intervals after you've entertained doing Welch's t-test versus regular t-test, those confidence intervals will not have the coverage that you claim. Simple simulation will show you that. You're failing to take into account model uncertainty. What about interactions? Well, we have to make these painful decisions. Do we include a treatment by covariate interaction in our main model or do we not? And Bayes says your struggle is coming from dichotomous thinking. We don't know enough to make a firm decision of an interaction being there or not. What we should be doing is the interaction's half in the model, it's half out of the model. So we have a prior for the interaction that specifies the amount of borrowing of the treatment effect across, say, between males and females. And there's an elegant paper on this by Simon and Friedman where they show you how to do a 2x2 factorial design with the Bayesian specification for the interaction prior. What about clinical and public health significance? With Bayes, you just compute the probability that theta is greater than epsilon for all possible epsilon. And Every reader will have a different epsilon that they're interested in. Just give it all to them. What about regulatory evidence for drugs? So this is what regulators care about is their error rate. And they think alpha has something to do with that, and it doesn't. So they're trying to make sense of multiple separate null hypothesis tests. I'm sorry, I was skipping ahead. I'm going to come back to that in a minute. That was regulator regret. So let's suppose you approve 5 drugs with these p-values, and you wanted to know what your long-term accuracy is in those decisions. So you want to know the track record. You can't get that from here. But if you had these posterior probabilities that were used in approving a drug, you just calculate 1 minus those, you sum those up, and that is your long-term success probability or error rate. So in those 5 approval decisions, you expect 0.2 of those to be wrong. So that would be how you calculate long-term success probabilities. It just can't be obtained from the frequentist approach. And so this is how we deal with multiple outcome variables. And so it changes your thinking. So what you do when you have multiple outcomes is you decide what condition would make us want to recommend this therapy. So in this particular example, the condition we put in a grant proposal was that either condition A is satisfied or condition B was satisfied and at least one of these was satisfied. And so A is any reduction in mortality. So if you achieve that, you're good. If you don't achieve that, is it non-inferior with regard to mortality? And did you either reduce the infection rate or the rate of infection or death combined? Did you reduce those? Or did you have a very nice improvement in performance status? That's actually more of a non-inferiority thing. So you just write down what would change clinical practice when you have multiple outcomes that you're assessing, and you calculate the posterior probability that that combination is true. So this is where Bayesian thinking is drastically different from how we handle multiple outcomes. So, and then there's differences for missing data. Mainly Bayes is doing a model-based procedure. There are Bayesian approaches to merging experimental and observational data. You can't do that in the frequentist world. We don't know how to do it. In the Bayesian world, you have 2 ways to do it. You can either develop prior distributions from the observational data or actually analyze the observational data in a joint analysis with the raw data of the observational study with the raw data of the experimental study. That is going to be the superior way to do it. So with Bayesian, you can have models that are sequences of models, and then you have shared parameters across the different models. High dimensional data. So very briefly, people use Lasso for high dimensional data. That's a convenience choice because it's fast to compute. The penalty you use in Lasso doesn't make sense. And if you have a very big effect, you'll penalize it too much. And so the Lasso is using a Laplacian prior distribution, which is this one here. It has this peak there at 0. And if instead of choosing something for computational convenience, you think about the problem and you choose a prior distribution that really reflects the family of effects in your genomic or proteomic problem, you'll select a prior distribution that is much more sensible, and it doesn't have this problem of downweighting truly important things that Lasso does. So that would be, for example, the horseshoe prior, which goes to infinity here, and it doesn't bring the penalty so severely for the big values. And so your posterior distributions for a horseshoe prior might look like this, and for like a normal distribution prior would look like this. So the other point here is when you're doing your inference, these are all posterior distributions that are classic posterior distributions. The fact that you use shrinkage gives you no concern. But when you're doing things like the lasso, we don't really get our inferential tools when you're doing penalized maximum likelihood estimation. But in Bayes, it's just a posterior distribution. So Bayes' formula allows you to use simple multiplication without complex sampling distributions. Bayesian thinking is the most important aspect of Bayes, and it's all about problem solving, quantifying evidence for things you don't know from things that you do know. And Bayes is all about avoiding unobservables and answering direct, relevant questions. So more information here, and I welcome your discussion and criticism. And I've hoped I've upset everybody just by the perfectly calibrated amount. So thanks for listening.
Talk over the multiplicity a little bit. So if you look for, with the example you showed, you had data from the football NFL. But if you look early with the Bayes approach, would you have to increase, the posterior probability 99.9 to protect against that?
No, easy no.
Because how do you take account into the random high? Say there's a random high early treatment effect, but it's not, it hasn't stabilized. If you were to stop at, posterior probability of 90, there'd be more chance that that's a wrong decision to stop compared to, so would you have to alter that posterior probability to do that given a random high?
You don't. And so I've got a couple of online articles about that, just showing with simulation. The bottom line is when you calculate a posterior probability at the end of the study using your prior, that works fine, but you're using the same identical calculations at any point before that. So the prior will have more weight early, and it will make things a little more conservative, for example. But the posterior probability is not only calculated the same way at every point in time, it has the same exact interpretation at every point in time. And so the bottom line is when you simulate data and you say, we're going to stop when the probability of efficacy is 0.9, and then you follow those studies to find out what you know, or you reveal the data generating mechanism, you find out it's really 0.9, independent of the frequency of looks.
Right, so for one of the slides, you showed that you had 5 drugs, and then that the probability of, we expect that 0.23 out of those 5 drugs will have, that's the error rate. But then I am getting a little bit confused because then that 0.23 is not a probability of making one error.
It's the expected number of decision mistakes
Okay.
out of 5. So you're operating at a 0.23 out of 5 decision mistake level, which is not bad.
One question that we have from online, if you could repeat the question.
Oh, yes, sorry.
Then when you do it this way, what about sample size? Is there like a way that one, given the prior, then you calculate the sort of optimal sample size that you need to make a decision, like have a posterior probability that will give you, a conclusive answer?
So the question is, how do you think about sample size and what's going to give you a conclusive answer? So if you go to this link here, there's a link to a URL that ends with the word design, and it goes through a detailed simulation of this. The fun part of it is you can decide whatever criteria you want, and you can find out what sample size will give you an answer. And the answer might be high probability of inefficacy, high probability of similarity, high probability of efficacy. And then you can, as I did in that simulation, you can add another criteria. That is, if you don't stop for inefficacy, you need the precision of the treatment effect to be better than a certain amount. So we not only want to have evidence for efficacy, we want to be able to state how efficacious the treatment was. So you can put a precision criterion into Bayesian very easily, but then you can solve for what sample size. Let's say you want the Bayesian power to exceed 0.9 at an expected sample size, or do you want it to exceed 0.9 at the maximum budgeted sample size? You have to decide about that. And then whatever you decide, you can simulate and solve for n such the probability that the posterior probability will reach 0.95 at the planned end exceeds 0.9. That would be what I call Bayesian power of 0.9. It's actually much easier to do. It may take longer to run, but it's easier to do than frequentist power.
So we have a question online. It's, first of all, it's from Mara Kuchi. She says, thank you, you made my day. Number two, she has a request for a tip. The fact that the trial sample size is a random variable scares funders. One way to get around that is to provide a frequentist sample size calculation to give an idea of the size. Otherwise, you go with a Bayesian sample size calculation that people tend to not understand. So what is your advice? Can you please repeat the question? What is your advice then on?
So that I don't know if people could hear what you said, but they were asking about Bayesian versus frequent sample size and how do you come up with a sample size? Okay, so we had a grant proposal we put into PHRI, which is one of our, they do more, I guess you could call practical clinical trials. And we had Bayesian power calculations throughout, but we included a frequentist power calculation for reference. And the reviewer criticized us severely, saying you've added nothing but confusion to this grant proposal. You need to use, if you're picking Bayes, it should be Bayes. But to answer the real question, you have the real solution to this is to have platform trials and basket trials. You should have multiple trials going on at the same centers and the same coordinating center so that when one trial is stopped early, you can move resources to another thing within the same system. That's the real secret, because if you use Bayes to its fullest, you're going to be surprised how early you know that something's not going to work. But then you're going to leave people unemployed if that's the only trial going on. But then the other answer is you have to say, here is the Bayesian power if we have this planned maximum sample size. Here's the Bayesian power if our simulation shows that our expected stopping time is going to be 40% of the maximum. And the Bayesian power in that situation is X. So you can imagine what the grant reviewers are going to be interested in. And you might be quoting them a maximum sample size, and you might be quoting them an expected sample size. And then you have to do the grantsmanship to decide which of those to emphasize. But they're all fairly easy concepts with Bayes. You just have to define your goals. Yeah, good. Okay. So this is from Lahana. One of our colleagues, Devereaux, often finds it hard to understand why Bayesian approach is advocated in cases where the sample size is small. His argument is that we have evidence showing that using a small sample size increases the risk of imbalance and key unobservable prognostic factors. So using an approach in this space that doesn't require a large sample is somewhat hard to understand. Well, I really don't like the premise of that question. And I'll say why I don't like it. When you calculate a p-value, it has the chance of imbalance already factored into it. So the imbalance issue should not really be mentioned in that context. So the p-value is taking care of all the randomness that can happen, including imbalance. So the thing about covariates is really adjusting for outcome heterogeneity, not dealing with imbalance. That's the biggest thing. So I don't really follow the idea that we need to worry about imbalance in certain situations more than in others. And also, if you use modern randomization techniques, and you knew which things you want to imbalance, you can enforce that and have perfect balance in your study. So not leaving anything to chance. And that's not really a Bayesian or frequentist issue. That's a general covariate balance issue. So I don't think the idea of being able to do small trials with Bayes, of course, the only way you can make them very small is to have a lot of prior information. So I don't think having small trials per se is going to be a game changer, going to be anything to worry about. And then Rob Balshaw, who I talked to quite a lot, would have thought that the sample size is random issue and not that different from planning survival studies based on number of events. It's just a random issue more than we think it is, because when you're doing a survival study, planned on number of events, the calculation we do uses an MCID that's a single number. And I think there's more papers coming out showing how to do what they call assurance. So assurance means you have a prior distribution for the effect size, and you do Bayesian averaging to get a certain frequentist power. So assurance is not a Bayesian power, it's frequentist power, but it's average over uncertainties of the effect size and possibly other things like standard deviations. So I think that's just showing you how to bring more uncertainty into the calculation in a proper way. But as I tried to say earlier, a Bayesian approach doesn't need any sample size calculation whatsoever. So you could just start with the first patient and keep updating continuously. And if you were self-funding something, or you were a pharma companies do this a lot with phase 1 studies. You know, they don't really need, they can learn on their own. They're not doing pivotal studies for the regulatory review. And so they can do studies without sample size calculations at all. They probably don't do that very often, but they certainly could, and nobody would criticize it. So it depends on your goals. And the best study will not have a sample size calculation. The best study will say, we don't want to assume anything that we're trying to learn from the study itself. And by refusing to have a sample size calculation, you'll be true to that belief. And you'll drive your budgeting people crazy. So when you have a different budgeting process, like there's some budgeting processes that budget portfolios, and that's actually much more rational to have a portfolio budget. So like you do within a pharma company, they have total control of the portfolio, so they can move resources around and quickly get out of things that don't look promising. Yeah.
So if we stop at study early as a basis, are you able to conclude saying that this is not?
So the question is, are we going to declare futility often in a Bayesian approach? And are we going to have situations where there just wasn't enough power? And so I want to change the nomenclature. So if you go online to one of these links, the one that has design in it, in the link, you'll see that I think a better word for futility is inefficacy. And so when you look at the simulation that I did there, the number of times that the trial was stopped, let's say you do 10,000 trials, you're simulating, the number of times the trial was stopped early for inefficacy was huge. It was like half of the 10,000 trials were stopped early for inefficacy. Very few of the trials were stopped, went to the completion of the planned maximum sample size with no conclusion. So what makes you go to the end with no conclusion is that the data are very marginal. They're right at like the MCID. And you don't know, you just don't know anything. But the fact that you can stop early with a conclusion of inefficacy is good news. And if you found out, if you ran the simulation that I ran, and you found out that instead of 1% of the time getting to the end with no conclusion, like I did. If you got to the end of the study 20% of the time with no conclusion, that means you violated the flow chart that I showed before that. The flow chart shows how to pick the MCID, and it says that you need to pick the MCID without reference to data or budget. So there's a loop in the design where at one point it says if your planned maximum sample size will not detect a certain MCID, you stop the study before you start it. In other words, you declare the study futile if the investigator cannot get enough budget to have a high Bayesian probability of obtaining evidence from that design. So there's a loop in that design. There's two things you have to loop through. You have to loop through selecting the effect size, and you have to loop through selecting, there was one other design characteristic, selecting the outcome variable. So I actually put the outcome variable in the loop. And if your study would go to the end with no conclusion, you can't use that outcome variable. You have to have a different outcome variable. So if you look in this Bayesian flow chart, in that link, it goes through all this stuff, and it's real easy, surprisingly easy.
Move this up here. Oops. Okay, here we go. There's two more.
Okay, so Lohan is asking another good question. I've heard argument of Bayes that you stop early for benefit. The evidence suggests trials stop early for benefit tends to overestimate benefits. So I've got a very simple example, and I should have put this in this talk because this is a great example of Bayesian thinking. So we know if you stop early for benefit because of a p-value being low, the treatment effect is biased high. And nobody corrects for that in any journal article I ever see. And there's medical articles saying you need to correct for that. What does the Bayesian thing do? So when you plot let's say the sample mean versus the stopping time, the sample mean will be biased if you stop early because the sample mean was big. It'll be biased high. If you plot the posterior mean as a function of stopping, it's perfectly calibrated at all time points. So what that means is the prior distribution is taking your data and pulling it back. And it's pulling it back by exactly the right amount, no matter when you stop. So this idea of you stopped and got a biased estimate is strictly a frequentist idea. It doesn't apply to Bayes. I wish I'd included that graph. Okay, did we cover? Okay, yeah.
I read that post for the calibrated posterior mean, and the one thing I was a bit confused about was that you said that the prior pulls it back such that it remains calibrated to be along the diagonal. But wouldn't that require that I have to be really careful about how I specify my prior?
Yep. And early looks, you have to be more careful. It matters more at early looks. And so this gets into the bigger picture. So the question was, wouldn't have to worry more about prior? Does it pull back the early look estimates by the right amount? Is it well calibrated? And so when you get into Bayesian operating characteristics, a Bayesian operating characteristic that you need to verify is that if the prior that generated the universe of trials that you're simulating doesn't match the prior you're analyzing the trials with, and in that simulation that I referred to, it covers this issue. You'll get a mismatch in your posterior probabilities, and your posterior mean will be disagreeable to a certain observer who uses a different prior. So instead of showing alpha for a Bayesian procedure, the logical thing is to look at the Bayesian operating characteristics And the number one Bayesian operating characteristic by far is the probability of making the right decision. And so the probability of making the right decision will be exactly what you say it is if the clinical trial simulation you're doing is generated by the same prior you analyze, but you do a simulation where they don't match. And so when you're quoting the Bayesian operating characteristics, you quote them conservatively. So if the prior matches, if everybody agrees on the prior, nobody criticizes it. And if we stop early, the decision we make is correct 96% of the time. That would be a typical number. Versus if there was a discordance between the priors and the decision you make was only right 91% of the time. So you would emphasize the 91% as your Bayesian operating characteristic because that's your worst case. And you would say to the reader, 91 is damn good. I'm not ashamed of it.
I had a question, and what's one of your thoughts on this? The way when you were teaching introductory courses on statistics and you're going on statistical inference, you tend to make this analogy that the court system makes this assumption that you're innocent until proven guilty. And so isn't that the same thing as the frequentist approach of saying, I have this null hypothesis that you are innocent until I get enough conclusive evidence that points me in the direction of being unlikely that you are innocent, so therefore I reject innocence. How would a Bayesian court system work?
So the question is, in the legal system, if it's a criminal case, innocent until proven guilty, is that like a null hypothesis? And is that kind of a frequentist setup? And I haven't thought about that enough, but I get the feeling it is kind of a frequentist setup and it's not optimal. So the optimum decision would be one that has the highest probability of being correct. Now that's assuming you're willing to convict, a few innocent people. So the question is, if you look in a civil procedure, is that really a Bayesian place? I think it's probably totally Bayesian, civil court case. So there's probably a difference between criminal and civil that would be worth exploring. Yeah, some countries it's preponderance of evidence, which is very Bayes. You're guilty. So this would be a great thing to explore. And I'd like to know, I don't know enough about the law, but it'd be nice to know how it fits in. But we do know there are cases, and they've been documented, where juries and judges have made impossible decisions. There was an article in the American Statistician about 20 years ago, how a judge made an impossible decision. It involved a handgun and a logical contradiction in the judge's thinking that made the judge's ruling impossible to be correct. So that's worth looking at for maybe a different reason. And we also know, like in the famous O.J. Simpson case, the juries misinterpreted evidence. So the DNA evidence was overwhelming. And so if you asked the jury, what is your prior probability when you came in to the courtroom the first day? The prior probability that O.J. Simpson was guilty would have to be below something like 0.01 for the DNA evidence not to give you a posterior probability of like 0.99. So there's no rational bias that a juror could have that would make the DNA evidence not sway someone, but that bias was there. So that's an illogical situation that Bayes would have prevented, but maybe that's not how the law works. Thanks for having me. It's been a pleasure. And thanks for the great questions. I got to sit down before my back.
Thank you. Amazing. Thanks so much.
Thanks, everybody. Yes, I got to stop sharing here.
See if I can log off so nobody knows that I'm.
That's right, you've been here. Let's see, end the webinars first.